So now as CTO of Nanosurf, he can tell us more about some of the recent development and transformation happening, especially related to nano-electrical characterization. So Dominik, we are very much looking forward about this new development. Please go ahead.
Thank you. Thank you for the introduction. So in about 10 days, it will be 1 year that I am at Nanosurf, and it has been a really exciting year with so many things going on, and I would like to share some of those with you today. For those that don't know Nanosurf, I would like to start with a little introduction on Nanosurf. So Nanosurf started in 1997 as a startup company from the University of Basel. And it grew by today to more than 60 employees with locations, with 9 different locations internationally. Some of them are just sales offices, but we also have R&D offices in Germany, for example. What we offer is a huge range of different AFMs. They go from what was the first product, basically a tabletop STM, to what you see here on the right side, nearly room-filling instrument for industry that can handle huge samples. And this is because all of our instruments are tip scanners, and that allows you to handle huge samples much more easily than if you actually had a sample scanner, which would be nearly impossible. We have customers that have 1 ton heavy samples, for instance. But what might interest this audience more is the research grade AFMs, which are these 3 here. So we have the core AFM, the flex AFM, and newly released the DriveAFM. So the DriveAFM also comes with a new controller. It's the CX controller. And for people that are interested in electrical measurements like KPFM, that might be a really interesting product to look into. But let me describe a little bit more what the DriveAFM can do and what is special about. So again, it is a tip scanner, but what is special is that for the first time, actually, we use piezo's to drive it and not electromagnetic actuation. And we have a patented design of an assembly of mirrors that are mounted on the scanner, so that the whole mass that you move is relatively low. And that allows us to actually put all the optics, meaning the light sources and the photodetector, off from the scanner. With that, we can also motorize it easily. So we have in the scan head, we have 11 motors right now. And with these 11 motors, you can automate the laser alignment, for instance. You see this here. I don't know if you see your mouse pointer or how I make a mouse pointer. Here we go. So yeah, you see here in this video how the laser alignment happens. We have 2 lasers, one for the readout and 780 nanometers for photothermal excitation. See here in the middle, we call it clean drive, which Stefan already mentioned this morning as a method to excite the cantilever without having spurious peaks. The spot size is small enough that you can work with small cantilevers, and that actually allows you to have less damping. This is very important when you work in liquid environments. So you can scan over cells and get the scanner that covers 100 times 100 times 20 in C micrometers. And at the same time, it actually gets the higher resolution. You see here 2 DNA strands where we can resolve the major and minor grooves quite nicely. Also shown at the bottom, the HOPG lattice can be resolved on a 100 micron big scanner. The DriveAFM is compatible with most of the accessories that Nanosurf developed over the years. So you can, for example, do fluid FM, or you can have heated sample holders, etc. It comes in 2 flavors. So for material sciences, it comes like shown on the left-hand side, but for biology, it's also possible to mount it on an inverted microscope. And this is the first instrument which has photothermal excitation on an inverted microscope, which is pretty important for stable bioimaging in liquid. So I want to stop my commercial break here, but if you're interested, if you're intrigued by the instrument, if you want to know more, let us know. You can also go to the homepage, request a demo, and we're happy to answer your questions and show you the instrument. But now to nano-electrical characterization at Nanosurf. So I don't think I need to motivate you guys why nano-electrical characterization is important, because it's used in so many fields and you all know it. But when I really think this is one of the three pillars of an AFM. First, we have roughness measurements or height measurements as the first pillar. We can have nano-mechanical characterization as the second pillar, and nano-electrical characterization as the third one, where there's actually no real competition, because you need to actually touch a surface to get a current from a sample. So I really think this is very strong for AFM, and that's why I also want to push that more. So I did my PhD, finished my PhD in 2009 on KPFM, and I felt like, oh, this is a dying technology. It's just a couple of groups that do KPFM. But when you now look back, more than 10 years back, you see that KPFM is actually growing quite a bit, the number of publications. We have about 16% growth in publications in nano-electrical characterization. And that is much bigger growth than if you just look at AFM growth or general publication growth. Like, let's say if you just put physics as a keyword, you get like 5 or 6% growth general in publications. And so at Nanosurf, we are currently pushing all of these, or having all these techniques, but I split them in two. We have on the left side KPFM, PFM, and MFM. That's methods where you measure a force. So in KPFM, obviously it's an electrostatic force that we measure or try to nullify. And in PFM, we actually measure the sample height, so maybe a repulsive force that we get from the sample. And in MFM, which you might say is not pure electrical mode, yeah, we measure magnetic force. Then on the right-hand side, we have SMIM, SECM, and conductive AFM, where you actually measure an electrical current. So in SMM, we apply gigahertz excitation and measure, that allows us to then, looking at the back reflected signal, we get the impedance of the sample. And so we can draw conclusions on the conductivity or dielectric constants. Then in conductive AFM, we just measure conductivity at much lower frequencies. And we can, for example, do IV curves. And if you want to do electrical measurements in liquids, well, there we can do electrochemistry, which is basically doing conductive AFM, but you need to run a potentiostat setup. And you also need to have specialized cantilevers. And so how, or what is going on at Nanosurf right now is that we want to push KPFM and PFM, and we do this together with Zurich Instruments. So we'll talk about this in the first part of my talk, and in the second part, I will talk more about hardware developments which are required for pushing the technologies on the right-hand side. I'll also mention some Python API that we developed recently that allows you to fully control your Nanosurf SPM over the command line. So in Kelvin probe force microscopy, as we have discussed a lot this morning, we apply a voltage and we try to nullify the response so that we have VDC equal VCPD. And the question is often, yeah, how do you do it best? Is it AM, is it FM, is it single scan, dual scan, or is it any of the other new modes? Many of those are great, but as an instrument manufacturer, how do you deal with that? Like, every customer wants something else, and it's really difficult to come up with one solution that covers all. And that was the reason why we teamed up with Zurich Instruments. This map here shows you what is compatible with what. We have the Flex AFM and Core AFMs that typically work with the C3000 controller. And we have the DriveAFM that works with the CX controller. But both of those controllers you can hook up to any of the Zurich Instruments logins. What this morning already Roma explained is how you can set it up. Basically, Zurich Instruments takes over the control of the voltages that are applied to the tip and sample and the Kelvin probe feedback, and Nanosurf takes care of the topography feedback and mapping of the signals. So here is a first result that we got with actually using first our AM KPFM off resonance method that we have implemented in our controller. The sample here is a semi-fluorinated alkane that's quite often used as a benchmark sample for KPFM. It builds this beautifully looking pattern self-assembled. And here in the middle and on the right hand side, you see the AM KPFM when we use the second eigenmode and a heterodyne KPFM, both using Zurich Instruments. And you can see that they just give nicer images. We have much less of this halo effect when we actually do FM. And I really think from my experience now playing with this, that heterodyne FM KPFM is a very neat technique that gives very nice results and very little artifacts. We have much more samples, and you can look at a webinar that you find on our homepage with much more samples, much more description of how we do KPFM. But for now, I would like to switch to a second topic, to the PFM, where we use the DFRT. And also this has been nicely described by Roma this morning. So when we actually look at the difference of the sideband amplitudes and use a contact resonance, we can apply much lower voltages, which is very beneficial to look at samples that are thin, like for example, the sample that you see here, that is a 2D material that has polarized domains. And when we apply too high AC voltages that are higher than the coercive voltage, which for this sample is below 1 volt, we would always depolarize and polarize the sample. But if we work with DFRT, we can actually measure it without this happening. Also, switching spectroscopy PFM is something we tried out, but we actually did not use the arbitrary waveform generator from Zurich Instruments. But thanks to our Python API, we could program our own signals. So this was done by an application scientist here at Nanosurf, who is not a programmer. It took him about 2 days to write a script that outputs these voltage steps and goes back to 0, and with the AC modulation on top of it. And he even built a whole little user interface that displays the data and allows him to run experiments, save data, process the whole data. So I think this is really powerful for people in this community, because you can actually really take control of your instrument. You can build new functionalities, you can experiment, you can make your own GUIs, you can process the data as it comes in. And yeah, it's a free alternative to MATLAB or LabVIEW, because you can use Jupyter Notebooks, for instance, to really make publication-ready pictures quite easily. So if you own a Nanosurf AFM, just type pip install Nanosurf and you're ready to go. It's really straightforward. If you want to learn more, you please go to our homepage under videos, webinars, under support. You'll find webinars on the Nanosurf Python APIs, and also there you find the advanced Kelvin probe force microscopy webinar that shows more samples, different measurement techniques that I didn't have time to mention. Also, there is a webinar on the Zurich Instruments homepage from last year, October, that Roma and Mehdi were giving on how to do Kelvin probe using their locking amplifier. So in the second part is much more hardware related, but we actually launched or are developing SMM in-house. So SMM is a technology that is often used in the semiconductor industry to actually do quality control or failure inspection of semiconductors. And how it works is that you apply in a gigahertz excitation to actually have this signal ending at your tip, you need to do proper wiring, meaning you have an impedance matchbox so that your signal really goes to the tip. And then you use a vector network analyzer to analyze the signal that gets back reflected. We have now designed a cantilever holder that really incorporates this. It has the impedance matching for up to 6 gigahertz. It's compatible with the solid platinum probes from Rocky Mountain. You can use this with a vector network analyzer if you own one, or you can get the Nanosurf custom electronics that will be coming out very soon. With the custom electronics, you actually have variable frequencies, so we can go from 1 to 6 gigahertz. And yeah, I think this is a very attractive solution, much less pricey than the vector network analyzer, of which most of the functions you actually don't need to just do SMM.
Dominik, so, you have 2 more minutes, please.
Okay. So here are some first results from SMM. It's a customer sample when you see the topography, and in the SMM results, you see the buried metal lines underneath. And on the right side, you see an SRAM sample, which is fairly standard, used by other AFM manufacturers too as a benchmark sample. If you want to learn more about SMM, there is an upcoming webinar on July 22nd. Then the last topic is, well, what if you want to do electrochemistry, or if you want to do nano-electrical characterization in liquid? There's many things you can do. You can do conductive AFM, you can do SECM, where you actually run a redox reaction between the tip and your sample, or you can do potential sensing, electrochemical AFM, and so on. There's many methods that are currently still evolving. But what you need to actually do this, to not have a lot of background from your cantilever, is you need a cantilever that is insulated. So my former company, Scuba Probe Technologies, when we developed these cantilevers, what is really special is that we use what we call a handle, which is a flex PCB that gets attached to the chip before we apply the full insulation. And then we just remove a few hundred micrometers from the platinum tip so that everything is insulated, and you can have reliable electrical contacts outside of your liquid cell. So you can collect currents that really come from the tip and not from anywhere else. So a few results here is that on a microelectrode array, when you map the SECM current while scanning over the surface, you can actually see which electrodes are biased. So in blue, those are the microelectrodes where you apply the voltage. So you always replenish the electrodes and keep replenish the reaction with electrons and keep the reaction running. And on the non-biased electrodes, we get no signal at all. Here you see another sample where we have a sequence of metal films deposited onto HOPG, and in the SECM signal, you can detect the different reactivities that you have from these metal films. On the right side, you just see what we offer at Nanosurf. We have a cantilever holder, which is compatible with these handles and probes from Scuba Probe Technologies. And at the bottom, you see an electrochemical cell that we developed just for this application. So I hope I could give you some insight on what's going on with, at Nanosurf. Many of these things are ongoing, but will come out pretty soon. And I hope I could also excite you about DriveAFM. If you have questions, again, please don't hesitate to contact us. We're very happy to scan over your sample or help you configure the instruments for your needs. Also, we are doing a redesign of our software. It will take us some time until we get there, but for that, I need help. If you know anyone that knows programming or anyone interested in working at Nanosurf, please let them know. We do have open positions. You can go to the homepage and look at the job ads there. Yeah, with this, thank you for the attention.
Thanks a lot, Dominik. Yeah, so I did not realize there was actually so many different applications you can do. And I like this 3-pillar approach. It's nice to see that KPFM is actually a growing field. So that's always nice to hear.